And there's an equation for calculating the force of some kind of charged thing moving in a magnetic field. That equation, F equals, well, let me double check and make sure that I give you the exact equation that your book gives you. QVB times sine of theta. It's the exact question that your book gives you. Okay. And the tricky part about this actually comes from another equation. This is from taking the cross product, F equals Q times V cross B. These are the same things. Did you talk about cross products in physics 1? You would have talked about them in relation to angular momentum. Did you ever do something with something called the right-hand rule in physics 1? Ever did the right-hand rule? Yeah.
No, I was so.
Fingers, bending, and thumb. So you were confused about it. So you've seen it.
Well, I was confused when you were on the power.
Okay.
Yeah.
You didn't learn any of that in physics. Okay. Okay. So here we go. We gotta pause. What is the equation for magnetic force of a charge moving in a magnetic field? Well, for magnetic force, what would that letter be? F is magnetic force. I'm going to put a little b down here too. If I have a charged particle, how do I denote that there's a charged particle? What letter is that? Q. And it's moving with the velocity. So what would that be? V. Magnetic field, what's that? B. And then sine of theta. So that's how you calculate the force of a charged particle moving in a magnetic field. What are the units of F? Newtons. What are the units of Q? Coulombs. V? Meters per second. And B? Tesla. Okay. What are the units of theta? Either degrees or radians. It's an angle, so degrees or radians. Depends on what your calculator is set up for. Okay, so that's how we find the magnetic force of a charged particle moving in a magnetic field. There's going to be other ways that we can calculate magnetic force. One of the things that we do with magnetic fields is we use it to control charges, to control where they're moving. And we often do this in what's called a cyclotron or a particle accelerator. So we can shoot particles in circles. And the way we do, when we do that, there's some physics that we can do to show how this works. But we're really, in here, concerned about calculating how big of a circle we can make things move in. And the size of the circle we can move in is R. How does R relate to a circle? What part of a circle is that? That's the radius. So that's basically half of the diameter, half of the size of the circle. And this is equal to m, little m, which is the mass of a particle, times the velocity that the particle goes, divided by the size of the charge of the particle, multiplied by b, the magnetic field that it's traveling inside of. So I can I can set up a magnetic field. Let me set up a magnetic field here. What are the two poles of a magnetic field? North and south poles. So I can set up a north pole and a south pole, and I can shoot a particle inside of here. And if I know the particle's mass and velocity and its charge, and there's a magnetic field here, this particle is going to go in a circle. And I can calculate what the radius of that circle is using this equation. Okay? That's kind of charged particle moving inside of a magnetic field. And we use this all the time. We use this to control where charges are going. If you have anybody ever had an MRI? What does MRI stand for? Magnetic resonance imaging. It takes a picture of your body, the insides of your body with magnets, and they're controlling how charged particles are moving using this equation. So this equation comes into play in MRIs. Really, really useful. Something else that happens in MRIs that we have to take account of. MRI has a pretty strong magnetic field. Actually, the MRI magnet its magnetic field is stronger than the magnetic field of the Earth. Do you know we have an MRI on campus? We have an MRI magnet on campus. Do you know that? Yeah. It's up on the 3rd floor. Except it's not set up to do imaging. Yeah.
Doesn't it say like you can't wear a watch or something?
Can't wear a watch, can't wear anything metal. There was recently a lawyer in Texas that was all about guns rights and obsessed with guns rights. He insisted on accompanying his mother for her MRI, and the technicians were like, okay, you need to take your gun out of your holster and you can't bring your gun in with you into the MRI room. He lawyered himself and said, oh, I'm allowed to do this. This is my right to have my gun. Now, personally, I think the technicians do have the right to tell him, no, you can't have your gun. If you get it near a magnet, it's going to go off and you're going to injure somebody. Guess what happened? They didn't make him remove his gun. He brought his gun in with the MRI, and what are guns made out of? Metal. Metal causes magnetism, so the gun actually went off and he ended up killing himself. Okay, so listen to your MRI techs. Okay, don't take guns near big giant magnets that are stronger than the magnetic field of the Earth. We do have one of those in this building. Something that puzzles me a little bit is how do you get a magnet that's super, super strong into a building, right? You don't make it in the building, so how do I take the magnet from the place where I make it to where I'm actually going to use it? You have to drive it down the road, right? But what else drives down the road? Cars. What are cars made out of? Metal. What do you have to put it into?
Rubber.
Truck. The truck is made out of metal. So what they do is they use something called an electromagnet. Electromagnet is only magnetic when you run electricity through it. And when you do that, you can get all sorts of crazy things that happen. And one of those things is this Hall effect. The Hall effect happens in electromagnets. So that's how we make those big magnets. It's something that only becomes magnetic when you run electricity through it. And the Hall effect tells us that you can create something called back EMF. And it's equal to B times L times V. EMF. What are the units of EMF? This is going back a couple chapters. Voltage. So this is a voltage. This is like a battery. So you turn a magnet into a giant battery based on how big the magnetic field is. B. What are the units of B? Tesla. L. What is L in the Hall effect? Length. So this is size of the thing that's creating the back EMF that's inside of the magnetic field. And then V is motion inside of the magnetic field. It's the velocity of your conductor that's moving. So that's the Hall effect. Creates this back EMF. And then that's not the only way we can calculate magnetic force. We can calculate magnetic force and back EMF of charges that are moving. We can also calculate it just based on a conductor, something that conducts electricity. So magnetic force on a conductor. And not the guy or girl or person that leads a band or conducts a symphony. This is a conductor, a piece of metal, basically. Magnetic force on a conductor, F, is equal to I times L times B times sine of theta. And in this case, the I here is current. Current, which you played with in your lab. How did the lab go?
Well, we didn't do the other lab before Ohm's law because it was broken.
You're in the late lab
Yeah.
and you couldn't get stuff working? Okay. But you started Ohm's law lab today or this week and that went okay? You got about halfway through? Okay. That's meant to take 2 class periods. If you ever have any feedback on labs, let me know, and I will do what I can to change things or give you more help. But you've worked with current in your lab. L is again the length of a conductor that's inside of a field. B is the magnetic field. And then sine theta is the angle between the current and the magnetic field. So it's magnetic force on a conductor. And we can take this and we can combine it actually with the magnetic field of a wire. So this is B field on a wire, not B force. Magnetic field on a wire. So if I have a wire and I set it up and I've got some current, let's say some current's going up through that wire. Anytime you have charge moving creates a magnetic field. You can hold up a compass to any wire in a building and that compass will move because there's wiring in the building. It'll move next to moving charges. You can calculate the magnetic field, how big it is, based on this. Mu naught times I, which is the current, over 2 times pi times r, where r is the distance you are from the wire. So if I want to calculate what the magnetic field is, say at this point, I can do that if I know what the radius is here. I can do that over here. Calculate what the magnetic field is, as long as I know the radius. The other thing we need to learn is another right-hand rule. If you want to calculate the direction of the magnetic field from a wire, there's the second right-hand rule. No shortcuts for this one, you have to use your right hand. There's going to be 3 things that we do. You take your thumb and you point it in the direction of the current. So what direction do I point my thumb? Up, down, left, right, up. So my thumb's going up. Then you take your fingers and you rotate your hand around so that your fingers are pointing to the place where you want the magnetic field. So if I want to know what the magnetic field is over here, then I would take my thumb and I would take my fingers and point them over here. Right? Point them on this side of the wire. So my fingers are pointing over there. And then you bend your fingers in the direction that your fingers will bend. There's only one direction my fingers will bend, right? They'll bend this way. What direction is that going? It's going in. And what direction is in? That's negative z. So over here, my magnetic field is going in the negative z direction. But it all depends on where you are relative to the wire. So what if I want to find the magnetic field over here? What direction do I point my thumb? Thumb's going up. Okay. I want to know the magnetic field on this side. What do I have to do? I have to turn my hand so that it's pointing over there. And then when I bend my fingers, what happens? It's coming out. So on this side, it's coming out. What would that be? Positive z. And now we got to get really trippy. We got to think in 3 dimensions because the world we live in is 3 dimensions. What happens if I'm in front of the wire? If I'm right here, if I'm in front of the wire, so I can't draw that. What do I do? Thumb's going up. What direction do I need to point my fingers? Towards you. And then what direction do my fingers bend? Bend this way. So what direction is this? Positive x. So if I'm in front of the wire, I'm going in the positive x. If I'm behind the wire, I'd be going in the negative x. Okay. So that's the second right-hand rule. You use the second right-hand rule when you're figuring out the direction of B. If you're looking for B, use the second right-hand rule. Thumb, point where the current, or where you want the magnetic field, and bend gives the direction of the B. Yes, sir.
So for when you're finding B field, thumb's always up?
Thumb is always the direction of the current.
Oh.
So we could do, let's do another example. Go off book a little bit. Let's do current. Do you want the current going to the right or to the left? Right? Okay. So if the direction is, current is going that way. Let's say, do you want the magnetic field direction above or below the wire?
Below.
Below? So if I want the magnetic field below the wire, I take my thumb, point it in the right direction, and then I need to get a step ladder so I can stand up taller, but I need my hand pointing down. I need my fingers pointing down because that's where I want the magnetic field. And then when I bend my fingers, where are they going? Into the board, if I'm underneath the wire. Okay?
Oh,
Think of it like this. Take my thumb is going that direction. Fingers point below, bend them, they're coming in.
so then to the left is
If the current were going to the left,
positive.
if the current were going this way, then underneath the wire it would be coming out towards you. But if it were above the wire, it would be going in. It's very flippin' crazy. Usually the day after physics students are tested on this on exams, they're all going to the PT clinic to get kind of PT on their hands because they contort themselves and injure their bodies. Okay? So that second right-hand rule is only when you're finding where the B is going. Use the first right-hand rule when you're finding the force. And we can actually find the force between any two parallel conductors by using the two equations I just gave you. So F equals I, we'll say of one current times L, I think it was times B. So that's force of one wire. And then let's say we bring it up next to another wire that has a magnetic field. We'll say magnetic field due to some second wire is mu naught times I2 over 2 pi r. So that looks something like this. One wire has some current going in it, I1, and then we have another wire with some current going in it, that's I2. And they're going to interact with each other. Two magnetic things, two things with charges flowing through them, they're going to interact. They're going to either attract or repel. And we can calculate what the force of attraction is between these two by doing this magnetic field is the magnetic field that this first wire is going to experience. So I can plug this B2 in over here. So I can get that force 1 is equal to I1 times L times B2, which would be mu naught times I2 over 2 pi r. And your book does this in a slightly different way. Your book says force 1 over length, so it divides both sides by L. Let's do that. Divide both sides by L. The L's are going to cancel out. And then this is the equation that your book gives you. Mu naught times I1 times I2 over 2 pi r. This is the nice thing about physics. Sometimes it builds on itself. All the equations are all consistent with each other. So this is the force between any two current-carrying wires. Force per unit length is equal to mu naught times I1 times I2 divided by 2 pi r. Combination of force and electric field. Super, super useful. And then one more thing to talk about. I want to talk about and ask a question on something called a velocity selector. One of the most practically useful things in all of physics, all of science, biologists use these, chemists use these, all scientists use these things to make charges go where they want them to go. So I'm going to set up two plates, positive plate on the bottom, negative plate up top. That's going to create an electric field. Where does the electric field go? Up, between the two of those, yeah? So that's the electric field. And let me say I take a positive charge and I'm going to shoot a positive charge into this field. So now I have some charged particle moving inside of an electric field. Where is that particle go? Where is that charge going to go? Is it just going to go straight through? No, where's it going to go? It's going to go up. Why is it going to go up? Because it's attracted to the negative charge, right? So it's going to try to go up. So it's going to kind of arc up like this. And what is actually pulling it up? What kind of force is pulling it up? Not magnetic. I don't have any magnets there. What do I have? I have an electric force because it's in an electric field. So I'm going to have an electric field that pushes it up, feels the electric force Fe. Okay. If I want this to travel through completely straight, I can put in a magnetic field here too. So what direction do I want the magnetic force to go? I want a magnetic force to go down. I can calculate how big all these forces are. I know Fe is equal to charge times electric field. I know Fb is equal to QVB. I want these two things to balance each other out, so I can set the two forces equal to each other. So that's QE equals QVB. Do I care about the size of the charge? Nope. Q's cancel out. So I can use this and I can calculate, oh, if I want to control how fast something goes through an electric field, it just depends on the size of the electric field and the size of the magnetic field. Now my question for you to figure out with the rest of class is to figure out what direction does the magnetic field that I create go? I'm going to give you some help with this. We have this equation F equals Q times V times B. Let's establish what direction V is going. What direction is V going? To the right? So that would be what? X, Y, Z. Positive X. It's going in the positive X direction. And then I need to do the right-hand rule to figure out what direction B is going. That's what you have to figure out. And we'll give you the direction of the magnetic force. So this is a little different than what we've done. We've already always known what V and B are and figured out where F is going. Now we know where B is going and we know where FB is going. What is FB? What direction is the magnetic force? It's going negative Y because it's being pulled down. So you need to figure out what direction B has to go so that I get that result. You should be able to narrow it down to a 50-50 chance. What are the two things that you could potentially choose? It's either positive or negative Z. So figure out which one of those it is. And I'm going to set up an electromagnetic rail gun and show you a physics demo. Okay. So work on homework problems. See if you can figure out what direction this magnetic field is going, and we'll go from there.
So this is the first